All right, recorded is rolling. It is Monday, December 12th. We're going to continue with the midterm review. You guys remember back on Friday, we did half a PowerPoint presentation. We're just going to do the other half of that today. I have given you guys this half-page midterm review with about 100 questions on it. So we're actually going to explicitly cover these questions starting tomorrow. If you don't have this for whatever reason, then here's a couple extra copies right there. You need one, if your apps of the day, I gave that out. Check out that. It's also on Google Classroom, all the documents. Your guys' rotational dynamics quizzes are back in your folders. If you want to pick those up. And here's a top scientist for rotational dynamics. You guys did really good on that. It's a good way to go into the midterm. So way to go right there. You guys know that this week is Spirit Week. I'm seeing some cool hats and socks out there. Tomorrow is Ugly Sweater Day, and then we got some more days going on. This is on Google Classroom. If you want access to this. Let's look at the midterm schedule real fast. You guys know your very first midterm is this Friday. That's going to be whatever your 7th period is. So you guys have 7th period here in a few days. Then we're going into the weekend, and then next week is a 3-day week leading into Christmas break. And then you'll only have a couple of classes each day. And then, okay, since you guys are 6th period, this class will actually be the very last midterm that you guys are gonna have. Okay, so there you go. All right, so let's switch over to computer screen and get this PowerPoint going. Okay. Don't know exactly the slide I left off on, but we're going to pick up here. So there may be a couple that I did back on Friday, and maybe a little bit of overlap. But here we go. So block in equilibrium on an incline. Try to keep kind of a good pace today. You guys know that this presentation is on Google Classroom too, right? So you guys got that available there. Okay, so would you guys say that there is a weight that's pulling it straight down? I mean, if you don't have that force, you don't have any of the other ones. Okay. And see those dashed axes? And so usually whenever you see an object in an incline, you want to analyze it in terms of that direction of motion, parallel perpendicular to the surface. So I'm going to take that weight and I'm going to break it into sine and cosine components, right? Playing off that angle, which is equivalent to that angle. There's a support force from the surface called a normal force, which is equivalent to mg cosine theta. Now, if I stop there, that block would not be in equilibrium. It would actually be like those Hot Wheels cars that are accelerating down the incline. So equilibrium, I need some kind of force to check the mg sine theta. Actually, I need to modify when it's equal to there. But friction force would be definitely equal to mg sine theta for equilibrium. Now, if all you know is equilibrium, you don't know if this is static or kinetic friction, then it might be at rest or it might be sliding at constant velocity. Could be either of those. Elevator physics. So every elevator here has exactly the same weight. So same weight. But maybe there's a different tension force in the cable holding it up. So going from left to right, if the tension in the elevator cable is less than the weight, then it's accelerating down, which might be moving down faster and faster. Or it might be moving up slow to a stop. And then the one in the middle, equilibrium, this elevator might be at rest or it might be moving at constant velocity. Again, if you only have the free body diagram to work with, it's ambiguous. You don't know. Okay. Maybe it's moving really fast. Maybe it's moving slow. Maybe it's at rest. Maybe it's moving up. Maybe it's moving down. Okay. That's if the tension is equal to the weight. And then one on the right, if there's more tension up than weight down, there's a net force upward. So it's accelerating upward, which might be up faster, or might be moving down slow to a stop. Okay. Here's the tension in terms of the acceleration. Down here, you guys can derive that from free body diagram, Newton's second law of motion. Atwoods. You guys did a lab back in the day where you guys remember the pulley and a couple of masses. And I had you guys figure out this expression right here. What is the acceleration of the system as a function of the masses? That's what came out to. So the top box is just Newton's second law of motion. Second box is from a macro point of view, what the acceleration is for the whole system. Now that's the upward acceleration of the small mass and the downward acceleration of the large mass. Then if you zoom into each mass individually, that's what those third and fourth boxes are. Right? They're looking at each mass individually, which each have two forces on. And that's where the tension force shows up. So the tension force is internal to the system as a whole, if I didn't show up here, but for each block, right? If you take physics in college, there's a good chance that you'll actually be taught this opposite of the way I taught it. Like I usually teach this from a macro point of view, like go straight to this one. But you could start from these bottom two equations and do a system of equations and solve it that way. Modified at would. So what if there's just one mass that's providing the weight, right? The other one's just providing inertia, right? Or here, there's also a friction force. Now, when you guys did this as a lab, you guys had a simplified version because you guys slipped a Hot Wheels car under here, which made this friction force go to zero or pretty close to zero, negligible, right? And then you get this setup. So here's Newton's second law of motion. Here's Newton's second law of motion as it applies to the setup. And again, for you guys, friction was zero. Right? And then each individual block, say as an open system, might perceive something like this with an acceleration. Car brakes to a stop. There are a few slides in this presentation that have that exact same title. There's going to be one later today when we do conservation of energy. So different perspectives on the car braking to a stop. Now, from a dynamics point of view, we're really interested in what are the forces. So this car is going left to right, and I see bam, those three forces on it. One down, one up that balance out, and then a friction force, which is acting as the net force. Now, you guys know friction force is coefficient of friction times the normal force. That's true if it's kinetic friction. It can go up to that value if it's static friction, right? You guys know that normal force would be equivalent to the weight as long as it's a flat road, right? So you can make some substitutions and figure out the rate that the car can slow down. That's the acceleration of the car. Coefficient of friction times the gravity of the planet. Car turns on a flat track. Now, if the track was banked, it'd be easier to make the turn. Maybe you could use like a horizontal component of the normal force to help the car turn. But if it's flat, then what force is allowing the car to make the turn? What force? Friction. Friction. So here's what it looks like from above. Here's what it looks like from behind, right? Now, from above, you're missing the ones that are going into and out of the page, but from behind, you can see all of them, right? Okay. Weight down, normal force up, friction force, that's allowing it to make the left-hand turn. Okay. Vertical loop. So you guys remember had this cup on a string, put some water in it, and was wheeling us around on a loop, right? And a really classic question that could be paired with that is, well, how fast does this have to be going around the top to guarantee that the water doesn't follow the cup or it stays in a circle pattern? Okay? Because if it goes too slow, then it's all going to fall apart. Right? So you can figure this out with dynamics. Here's free body diagram at the top and at the bottom. Now I'm specifically interested at the top part to answer this question. So let's look right there. You see the net force is the sum of those two forces, the weight pulling down and also the tension pulling down. But here's what I do. I'm going to say if I'm interested in the minimum speed just to barely get around, I'm going to let the tension approach zero right at the very top. So there's it goes to zero. And the net force I'm going to say is acting as the centripetal force, which in this case is only provided by the weight. So you can solve for that V right there, and then you'll get that expression, square root GR. You guys remember doing this back in the day? Right. Now hold on to this idea because this is going to come back a few slides from now. You guys are going to see a roller coaster, and this is going to be the first part of two parts to answer a roller coaster question. Pendulum swinging. I'm thinking there are two forces, the weight straight down and the tension kind of up and to the right in that case. Right. Now, if you add those vectors tip to tail, you get this brown dashed net force, right, which is not a unique force. It's just the sum of the forces, right? That's what the net force is. Right? Now you guys see how that net force is like tangent to this circle pattern that the motion of the apple. Okay. Now, what's ambiguous there is the direction that the apple's moving. It might be moving down to the right. It could be, right? Or could be actually be moving up and to the left. So what is its actual velocity, its direction of motion? That's ambiguous. It could be either one. But regardless, the forces and the acceleration would be the same. Okay. Conical pendulum. So you guys can think 3D, right? You guys can think in 3 dimensions, right? So only two forces on this apple again. Right? It's weight acting down and the tension force up and to the left. Now, this time, if you add those vectors tip to tail, the net force is strictly horizontal. It's just like horizontal point straight in the center of the circle. Right? And here's the conditions that I have to set up. So there's zero vertical force. Right? If you do F cosine of this angle and the weight, those have to balance out, have to zero out. Okay? But horizontally, there is a net force because the fact that it's on a curved path. There has to be some kind of centripetal force. In fact, that's exactly like no, my computer screen's frozen. Timeout. We're gonna have to pause this. Share screen. Guess this one here. All right. Let's see if I think I have to slide this over here to make this work. Okay. All right. So we're right here. All All right, so this brown net force, which is really the sum of the two black forces shown there, which is the only two forces of the tension and the weight. Okay, okay, that is your centripetal force right there. Right? MB squared over R. Okay. Apple hangs in equilibrium. Okay, it's pretty straightforward. Spring force up, weight down. They have to balance out. Okay. You can make some substitutions, solve for stuff. If you know any three of those, you can solve for the fourth kind of deal. Here we go. What about like a truss joint in tension? You guys remember that day? This is a while back. I handed you guys some spring scales and a full page lab page. It had 10 mini labs on it. You guys remember that? And one of them that I keep referring back to over and over, it was this right here. Right. So what if you like hold them straight up and you make like a Y shape, like you guys are looking at, and you pull that out closer and closer to like a T shape? What happens to the spring scale ratings? Right? And what does happen? The more you make it, like right now, it looks like a Y. What if you make it look like a T? What happens to the spring scale ratings? They shoot way up. They can go way up, right? Okay. And here's the principle: is that the sum of the forces has to go to zero, and we're going to break that into vertical and horizontal components. Right? Bam, like that right there. You guys see how the two green components up and the weight down have to balance out? That's that green condition right there. And see how the rightward blue component, the leftward blue component have to also balance each other out like symmetrically, right? The right equals the left, right? Has to balance out, right? So, and then those components, those dash components, are really just the sine and cosine components of each spring force. Right now, here it's looking pretty symmetrical, so that looks pretty good. Right? If you know the angle, you could. But you can never make a perfect T shape with that. You can never make a perfect capital T, because there's always going to be some vertical components that have to balance this weight. If the weight of the apple is like 10 newtons, then this has to be 5 newtons and 5 newtons to balance out. Right? Now, those blue components can always get bigger. Right? The spring force can approach infinity, the closer you make it to a T shape. Okay. All right, rotational kinematics. You guys remember breaking out this turntable? I think you guys did some labs involved with this turntable. Give this thing a spin. Right? Now we're more interested in maybe not how far something moved in a linear sense of meters, but how far something rotated, which you can measure in revolutions or degrees. But more often than not, we used radians, because radians are best for equations. Like here, you have to use radians to plug in here, right? So how far is it turning radians? How fast is it turning radians per second? Okay. Another example of this omega could be the Earth rotates once every 24 hours. You could convert that to radians per second. Okay. And alpha is an acceleration, but it's how fast is the turntable speeding up or slowing down spinning, like radians per second squared. Okay. Now, if you park something on the turntable, like you guys remember I had 3 Roosevelts, boink, 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 and then the slide, you guys see some apples. Okay. Well, those might have linear kinematic values too, right? Like there's some distance they've got around X. If there's some linear speed, if you point a radar gun at them, and there might be some tangential acceleration. Okay? And you can translate back and forth between rotational and linear by multiplying or dividing by the radial distance to the center, depending on which way you're going. Right? Now, I want to emphasize on the screen that nowhere on that screen is centripetal acceleration. Right? There's linear acceleration, like tangential acceleration. There's angular acceleration, rotational acceleration. But what centripetal acceleration would be v squared over r, or omega squared times r. Right? That would be the acceleration involved with keeping one of those apples or coins on the surface. Right? Just like that. Oh, here's some rotational kinematic formulas. These are analogous to your linear formulas back in the day, like x equals v naught t plus half at squared, only now it's theta equals omega naught t plus half alpha t squared. Right? So time is still time, but now just like something like how far you're turning and so on like that. Right? Here's the same kinematic formulas, just it looks a little cleaner right there. Turntable slows to a stop. Ooh, you guys see I have 3 graphs set up, right? Theta versus t, omega versus t, alpha versus t. Right? So say I give this thing a counterclockwise spin and it slows to a stop. Right? So that's all the setup right here. Right? What are these going to look like? Well, I think let's start with this middle graph, because I usually start with the middle one. It has some omega, that's radians per second, and it slows to a stop that goes to 0 radians per second after some time interval. Now that's a really information-rich graph, because the slope of that tells you angular acceleration, like the rate that it's slowing down, which, hey, that's a negative slope. That's a negative angular acceleration. Oh, it's slowing down. Okay? And the area under omega versus t tells you like how much angular displacement it's accumulated, which if you break that up into time intervals, like 1, 2, 3 seconds, it looks like it's accumulating angular displacement. It's always positive, but it's like less and less rate. And so it's going to be like a downward curving parabola, sort of like that for theta versus time. Okay. So here's some fun trivia. You guys remember the old technology, the old LPs turning to constant rate, so the linear speed between the needle and the surface would change. Okay. But the newer technology, like CDs, they actually change the angular velocity, so it actually spins at a different rate over the course of the CD, right? So that they can pack more information onto it. So the laser goes at like constant linear velocity. Foucault pendulum. You guys remember if you have a pendulum swinging on the surface of the Earth, like really well controlled, then the Earth will rotate underneath it. Okay. So this works really well with the poles. It doesn't work at all on the equator. Okay. But from the surface of Earth, it looks like the pendulum is changing its orientation, but it's not actually true. It's actually the Earth rotating underneath it. Okay. A related idea is Coriolis effect. Okay. Now, this is if you're changing latitudes significantly, then the latitude you're coming from and going to have different eastward velocities. So there's a discrepancy there. And from the surface of Earth, say you like fire a cannon straight forward, if you're in the northern hemisphere, it's going to look like it's curving off to the east if you're changing latitude, either firing north or firing south. Right? Suppose you have a big low pressure system. That's what the giant L is, and it's like meteorology. That could set up a hurricane. That's why hurricanes form. They always spin counterclockwise in the northern hemisphere. Centripetal force. You guys remember doing this lab with PVC pipe and the Play-Doh canisters and the string? Okay? And you guys derived from scratch that the centripetal force, in this case provided by the weight that's hanging here, okay, is equal to mv squared over r. Here's your m, okay, here's the v, here's the r. Okay? You guys remember doing that? You could also say centripetal acceleration is just v squared over r. It just divide by the mass. That's Newton's second law of motion. So if you know any three of those, you can solve for the fourth, but also you can find things proportional. Like you can say, here, I was swinging this like 3 times this linear speed. If you triple that v, okay, then maybe you would need 9 times the weight here to hold it in place, right? Something like that. If you have a like a turntable or a neocylinder or one solid thing that's all rotating together, it's usually more convenient to set up centripetal force and acceleration in terms of omega, right? The rotation rate for the whole thing. Okay. Now the other equations still apply. Like for centripetal force is still mv squared over r, but m omega squared r has some advantages too. Like all these guys right here at the surface, maybe you want to spin this at such a rate that they all feel like they're on Earth. They experience 9.8 meters per second squared of centripetal acceleration. Oh, well, if you know the radial size of this thing, this is 9.8 meters per second squared, you can solve for omega, how fast you have to spin that to make that happen. How about this guy climbing this ladder? I know if he's right in the center, he feels 0 artificial gravity. Okay. In fact, he gives himself a little push off the ladder, he'll just like float off into space forever. Terrifying. But this equation backs that up, because if you plug in 0 for this radial distance from the center, you get 0 artificial gravity, right? Centripetal acceleration. And then if he's like halfway down the ladder, he'll feel like at this point right here, he'll feel like half of Earth's gravity. Kepler's laws, planetary motion. So Kepler way back in the day was looking at data from Tycho Brahe. He realized that planets actually move in elliptical orbits around the sun, not perfect circles. His second law says this idea about equal areas and equal times. And then third law he came up with many years later. He said, hey, if you look at the square of the time period it takes a planet to go around the Earth or around the sun. So for example, for Earth around the sun, this would be 365 days. That's proportional to the cube of the average distance from the sun. And then Isaac Newton was later able to take that information and help solidify universal gravitation, orbital speed, this sort of thing. So what you're looking at right here on the bottom right cell is a Newtonian update to Kepler's third law. Okay. Inverse square law, this is going to help set up universal gravitation. So you guys remember like intensity from a candle flame, like tapers off 1 over the distance squared as you get further away from it. Okay. Like if you're 3 times further away, you get 1/9 of the light. Okay. So that's a consequence of living in a universe with 3 spatial dimensions. Now that also works for universal gravitation. Okay, so you got 2 masses, they're going to gravitationally attract, but the force is proportional to 1 over the distance squared. So there's inverse square law showing up again. So if 2 say asteroids are like 3 times further away from each other, then you get 1/9 of the force. Okay? But then if you turn it around, suppose they're like gravitating towards each other. If they're like 1/3 of the distance, now that's 9 times the force. So the force is changing depending on the distance. Okay? You can use that to set up like an orbital speed, for example, because you might want to know like what suppose that gravity force was the only force on an object and it was acting as the centripetal force. Okay? You could solve for the orbital speed. Just do a little algebra switch around to get that. Isaac Newton thought about this as like blasting a cannon straight horizontal. How fast would the cannonball have to go to orbit the Earth? And it would be that expression right there. Okay? This next slide, I'm actually going to jump ahead a chapter just because the expression looks similar. Escape speed. Now, escape speed you can derive from conservation of energy. It looks like this, but there's it looks like orbital speed, except there's a 2 slipped under here. So if you know orbital speed, multiply by the square root of 2, that's the speed you would need. So that if you blasted a rocket straight away from the planet and cut off the engines, then it would have enough juice to just fly away forever. Okay? So there's gravity field surface of the planet, there's orbital speed for the satellite, and there's escape speed for that rocket right there. Boom, boom, boom. Okay? Eggshell planet. So if you found this planet that was a giant eggshell, kind of like basketball, it was empty on the inside, and you picked an arbitrary point in the middle, you can show that the force to the left and the force to the right exactly cancel out, and then everything up and down also cancels out by symmetry. So that is a gravity-free interior. Now that might seem kind of an abstract idea, but where this could actually be useful is suppose you are like tunneling down to an actual planet, like a solid planet, and you want to figure out, hey, what if I'm like a third of the way or halfway down to the center? What is the gravity pull here? Because I know at the center it would be 0 exactly. Okay? Does it scale proportionally with the distance? The answer ends up being yes. And you can show that one step is knowing this right here. You can know that everything above you in elevation is essentially just a series of shells that one by one will cancel out. Okay? So the only gravity that pulls on you is anything below you in elevation. Tides. So Earth has a couple of tides every day, mostly caused by the moon. The sun has a little bit of an effect too, but it has to do with there's a proportional difference in distance, close side and the far side of the Earth from the moon that's tugging on us. Okay? And then the Earth, okay, so the moon also experiences a tidal force, and the moon is actually tidally locked to the Earth. Lagrange points. These are points of gravitational stability. They're good opportunities to park space probes. Like NASA launched James Webb Space Telescope about a year ago, and that is orbiting the L2 point from Earth to the sun. It's right there. Forms of mechanical energy. So we're off to energy now. Energy. So energy can take different forms. These are the main ones we care about in physics. Next semester, we'll add thermal energy to this list, and we'll work with that too. But you guys know work, a transfer of energy is force times distance. Now that's a dot product. You care about parallel components. That's I think next slide coming up. Okay. But suppose you lift something. If you lift an object, you need to apply a force that's equal to its weight. And the distance you lift it could be the height you give it. So you've put energy into it that way. In fact, you've given it potential energy, which is exactly this next line, mgh. Right. So if you know the first line, you can get the second line. Right. Now that energy could come back if you like tip it off the shelf. It crash lands with some like kinetic energy, 1/2 mv squared. That's energy of motion. What else we got on here? Spring potential energy, 1/2 kx squared. You guys remember Hooke's law? I think it was kx. So the force to compress or stretch a spring is equal to kx, where k is the spring constant, x is the amount that you stretch or compress it. Right? But the energy stored is 1/2 kx squared. Right? Now those 4 yellow lines are the main building blocks that you care about for this class. Right? Let's throw in the green ones here. If you change your distance from a planet enough, that lowercase g, looking at potential energy, does not stay the same. Like if you're blasting a rocket all the way to the moon, you can't use mgh in your equations. It wouldn't really check out. Okay? So you have to use the more universal form, negative gmm over r. It's always negative, kind of abstract, great idea, but it checks out. Also, if you go from like the top of Mount Everest down to sea level, which is a small change in the big scheme of things. It's not very much compared to the radius of the Earth. Right? If it's a small radial change compared to the planet, you can show that universal potential energy simplifies to just mgh for small height changes. And the last one on this list, all the way at the bottom, rotational kinetic. So if something is rotating, there's energy involved with it rotating. And the simplest way to account for that is 1/2 I omega squared, rotational inertia, angular velocity, blah, blah, blah. Just pop it all in. Okay, work is force times distance. That's a dot product, which means you care about parallel components. So I've got a couple examples. Suppose you got forces and distances that are not parallel to each other. Bam, bam. Now we've got some parallel components. I like to imagine this cosine being attached to either force or the distance. So I'll give you an example of each, right? Attach to the distance here, attach to the force here, right? So as you're moving these objects around, you're doing work on those objects, right? You're transferring energy into them. Maybe changing height, changing speed, something like that. If you ever see a force versus distance graph, the area under that represents the energy transfer into or out of the system. So it could be the work done, energy transfer. Systems can be closed or open. If it's closed, that's just straight up conservation of energy. Energy is conserved. If the system is open, there might be a force on or by the system, so there could be energy entering or leaving the system. So say plus or minus work. Let's look at some examples of these. So real fundamental example here. Galileo drops a ball, Leaning Tower, at the top it's all potential energy, at the bottom it's all kinetic. So the classic question could be, how fast is it at the bottom? So you say that kind of energy is equal to that kind of energy. You solve for V, and oh, look at that, square root GGH. You guys would have known this from kinematic motion way back in the day. You guys remember VF squared equals V naught squared plus 2AX? That's completely consistent with that. Okay. Yeah, this shows up all over the place. This will show up next semester when we do Bernoulli principle. You have like a pipe full of liquid and you open it at the bottom of the pipe, it's a vertical pipe. How fast does the water shoot up? Square root GGH. See that all over the place in physics. So like you start from rest at the top. Block spring earth system. Oh, this one I like a lot because it involves several of those building blocks. So we're going to take this mass, we're going to squish it against the spring. So now this thing's spring loaded with some 1/2 kx squared. Then let it fly off. And that energy needs to both go into lifting this against gravity, but also give it some speed at the top. And it's got to have some speed to make it around the loop. So now you have this setup. This kind of energy turns into this plus this mix. Right? Then you can solve for stuff. If you know most of those variables except for one, you can solve for the one unknown. You know those things. This roller coaster. I promised you guys this one was coming up. So here it is again. What is the minimum height to guarantee that it gets around? Now we're going to assume no frictional losses. So this is like an edge case thing. Right? And I told you guys part of this involves trying to figure out, well, there's an associated minimum speed at this point at the top of the loop. Like if it runs out of juice, they're just going to fall off the track. Right? And that's something that we saw earlier. You guys remember V was the square root of GR, right? For like a cup of water, vertical loop. Right? So we got that. Right? Now, let's go on to conservation of energy and go ahead and finish this off. What is this minimum height? Right. So we've definitely got a complex problem here. That's all right. Because I know it's all potential energy at the top, but then by the time it gets to the final location, see, you have to climb this wall. So that's m times g times 2r, because the height of the circle is 2r. And it's got some kinetic energy left over, 1/2 mv squared. And oh, look at this, right there. V squared is gr. I can substitute that right there, like that. Just do some algebra cleanup, and bam. So that is the theoretical minimum height drop. It's always 5/2 times the radius, really classic physics question right there. Notice that the mass cancels out, which means that it doesn't matter if it's loaded with passengers or not. The gravity field cancels out. So once you solve this for Earth, you could take that exact system to Mars and it would be exactly the same. Pendulum maximum speed. How fast is it going right at the bottom? Well, conservation of energy. Now this might possibly have some complex steps thrown in between. You might have to do some geometry first. Would you guys be able to figure out that is L times cosine theta? Okay. And this whole, this height change might be important for conservation of energy, right? Is the difference between L and L cosine theta. And if you want to, you can factor in an L, make it look like that. Right, now let's do the conservation of energy setup. I bet it's potential energy up here and kinetic energy down here, maybe something like that. Okay. Boom, just like that. Oh, and then if you solve for our V final, you get, oh, it's square root 2GH. Okay. Square root 2GH with a couple of additions. So H is now this whole fun expression right here, playing off geometry. Okay. And one more detail, which is this gray text. Now the gray text is if you push off, right? So what if you don't start from rest? If you start from rest, you just scratch out the gray part, right? What if you do push off? Well, V final can't be the initial plus the square root of blah, 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 2GH. You have to be the square root of and throw the V squared inside. Right? So it plays out like that. Common mistake to make in this class, something like that. Okay. Oh, car brakes just stopped. You guys saw this title earlier today, and I think back on Friday too in a different context. So a really classic question could be, what's the braking distance, say as a function of the initial speed, right? Got the free body diagram, you guys saw that before. So I'm gonna treat this as an open system. That's what that says, right? Open system, initial energy minus the work equals final energy. But you know what? I think the final energy would just be zero, because there's no kinetic energy, it's stopped. There's no potential energy, it didn't roll up any hills, right? So had some kinetic energy to start with, and friction force times distance took that energy out, right? Left it with nothing. You guys know friction force is coefficient of friction times the normal force, and the normal force is equivalent to the weight. So bam, 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 just make some substitutions right there. You can solve for the braking distance, and it's always that right there. It's that expression. Got coefficient of friction, gravity field, initial speed of the car. Okay? Now, what I usually do, the question I usually ask about this is, I just care about two variables in this expression: the distance compared to the initial speed of the car. I'm going to pull that as a proportionality, right? That's like a partial equation right there, right? So a classic question could go like this. Suppose you triple the speed of the car. What happens to your braking distance? 9 times. Right? So if you're going like 20 miles an hour to 60 miles an hour, you need 9 times the amount of road to brake, right? Modified Atwood in terms of energy. Okay, this one's kind of fun. I'm going to do open system. I'm specifically doing open system because there's a frictional loss right here. Okay? What is the energy supplying for the system to move? And then what question we're trying to figure out. So maybe the question could be like, how fast is each block moving after this whole system moves some height change h, some distance h, guys that, okay? So conservation of energy. Now the supply of energy is the large block can fall. That's it. That's the impetus for this thing to move, right? The large block can fall. So that's what's in green right there, right? The potential energy, that's in green. Okay? This frictional force is going to zap some energy out of that system. So I'll do minus force times distance. Right? You could get more granular with that, you know, coefficient of friction, blah, blah, blah. Right? And what's left over is going to go, I'm thinking 4 places. It has to lift the small block, and it also has to give each of these blocks a speed. So boom, potential energy plus 3 kinetic energies, blah, 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 just like that. Okay. And then if you know some numbers, you can make some substitutions, solve for stuff. If that's a big picture, how you'd solve that. Okay. Mechanical advantage system, pulley systems. You guys constructed one of these in one of your labs. Right? Do you guys see it's 3 to 1? Because look at this movable pulley. Isn't it like the weight is split point, 3 different ways? So from the point of view of the spring scale, you feel 3 times as strong, or like up to 3 times as strong. Okay? If this apple weighs 3 newtons, you only apply 1 newton of force, ideally, to lift it. Right? Now the principle this works on, conservation of energy, is that work input equals work output. Right? You can't multiply the amount of energy in the universe. Right? You can multiply your strength. Right? That's what mechanical advantage is. Now the ideal mechanical advantage is just based on the geometry of the system. So here it's clearly 3 to 1. Right? But there's also the actual mechanical advantage, which you guys also calculated when you guys did this lab. You said, hey, if I take the ratio of the forces, let me see how close that is. Now that might be a little bit less than 3 to 1 because there might actually be some frictional losses in reality. Right? You could also have created a mechanical advantage using wheels, like a wheel and axle system. So same physics principle here, conservation of energy. And in this case, the mechanical advantage would be, the ideal mechanical advantage is the ratio of the radial sizes. You can make mechanical advantage that way. Right? Same actual mechanical advantage, ratio of the forces might be a little bit less than the ideal. You can also use an inclined plane to get a mechanical advantage. Right? This is going to be, all right, the screen's froze again. All right, let me do pause again. Pause. All right, recording's resumed. All right, let's get back on the boat. All right, here's some simple machines. Fun and new. Momentum, you guys know is mass times velocity. That's a vector value. It's conserved and it's used in collisions. Anytime you see a collision, think, guys, do something with this. Okay? Closed system could be momentum is conserved, a lot like energy is. This is a vector. Okay? If there's an open system, there might be an outside force, external force. So you can have a change in momentum called an impulse, right? Plus or minus, because entering a living system. Right? So general conservation of momentum, you have 2 things colliding. And what you can say is that the momentum bits before the collision have to equate with the momentum bits after the collision, mass times velocity, keeping everything on just the x-axis here, just one dimension. Okay. Now, you might start thinking, well, hang on, you can have lots of different kinds of collisions. Are we talking about bouncy balls or clay balls that fly and stick? Are we talking about like half to play tennis balls? And that right there can handle all of those situations. That will handle all of them. But let's get more specific. So next slide. What if they collide and stick? That's called perfectly inelastic. Right? And you can just modify a little bit, right? One common mass, or one giant mass, one common final velocity, right? Post collision. Okay? Or the opposite scenario, you might have like this Newton's cradle right here, where it's like really bouncy, right? And if it's really bouncy, then from a physics point of view, momentum is conserved, but also is kinetic energy. This is the generic solution, the general solution. You don't have to memorize it for this class, but it's good to know what that is and where it comes from. How bouncy is something? The physics term for that is called coefficient of restitution. So it's the ratio of post compared to pre-collision difference in velocities of two objects. Okay? Now, for bouncing a ball off the floor, and this is the lab version of it, so you guys did this version of it right here. You can figure out what those are based on the drop height and the rebound height. Oh, look at this, square root 2gh, right? For each one of those, take that ratio, right? And then you can get coefficient of restitution that way, like square root of the ratio of the heights. Impulse is a change in momentum. That is the area under a force versus time graph. Now, remember back a few slides ago, area under force versus distance was work, which is an energy change, but right, we're looking at right here, force versus time, we're talking about an impulse, like a momentum change. Okay? So change in momentum impulse is force, okay, mass times change in velocity, okay, which is average force times time. So looking at average force right here. You might have a triangle looking type graph going on. Ballistic pendulum. So here's another one of these complex physics questions. I'm saying complex because it's going to involve multiple parts. So what happens chronologically is that this bullet's going to slam into the block and it's all going to swing up to some height. Okay. But the most common question from this is, what is the firing speed of the bullet? And to answer that, you actually answer it in like reverse chronological order. So I'm going to start with the fact that this swung up to some height that is easily measurable. And we're going to back calculate how fast was the bullet going to cause the collision that led to this whole thing in the first place. Okay. So we'll start with the conservation of energy, just the bullet, just the whole bullet block system swinging up. Right. And from that, oh, look at that, square root 2gh, set it in motion to go up to that height. There's square root 2gh again, right? Keep showing up again and again and again in this class, right? Now we're going to go back in time and say, hey, what collision between this bullet and this block set that off in the first place? So it could go to that speed, right? How fast was the bullet originally going? So there's conservation of momentum, perfectly inelastic collision, and make a substitution right there. And there you go. Just like that. If you ever see a two-dimensional collision, I think I think you guys may have seen one of these. Okay? Then the principle is the momentum is conserved both in the x direction and in the y direction. So you set up separate equations, system of equations going on there. Okay. Center of mass. So this is mathematically, you can take a weighted average. I did a little bit of this. So suppose you got like a big apple and a small apple, and maybe they're like stuck on a stick together. Okay. Maybe that stick has negligible mass itself. You guys see that the point that it could balance on your finger would be about this dot right here, which is closer to the big mass. Right? It's like a weighted average. Right? So that's the point of the balance on your finger. Okay? It's also the point that you guys remember you had those foam boards, right? You guys tried this out in class, right? So if you hang the foam board, the string always hangs through the center of mass. So that's another way you can get it. And a third way you can get center mass is if you have one solid object and you throw it through the air and it's like spinning, it'll always spin about the center of mass. Okay? So in this case, here, you've got a general formula, and then here's what it applies to that specific scenario, simple taking a weighted average. Okay? So we're transitioning here into rotational dynamics. So let's look at some rotational analogs. Now, time is still time, but now instead of how far is something going in meters per inch and how far is it turning in radians, how fast in meters per second is now how fast is it turning radians per second. Acceleration has an analog, angular acceleration, like speeding up or slowing down spinning. Now, mass, before any kind of rotation, was just mass represented the amount of inertia, right? But now in rotation, we care about not just how massive, but where is that mass located? So that's mr squared for a point, okay? And sum of mr squared for a bunch of points. Okay? It's rotational inertia. I've got a table coming up next slide. Newton's second law of motion, F equals ma. The rotational analog is torque, causes rotational inertia times angular acceleration. Torque equals I times alpha. And you get a torque by applying R cross F. Okay? Momentum equals mass times velocity. Angular momentum is rotational inertia times angular velocity. Kinetic energy translational is 1/2 mv squared, and kinetic energy rotational is 1/2 I omega squared. Boom. And so here's rotational inertia table. So some common shapes. A point mass is mr squared. A ring is just a bunch of point masses, so it's also mr squared. But all these other ones, the mass is distributed closer to that axis of rotation, so it's less than mr squared. Parallel axis theorem. What if you have something that's both rotating and revolving? You can do its original rotational inertia about its central axis plus that mass times axis of revolution squared. Okay? So example could be a ball rolling across the floor, right, where it's rotating about this point down here. So the distance d in this case is its own radius, so you get this modified rotational inertia for like rolling. Okay? Torque, you guys know, is r cross f, which is rf sine theta, right? You multiplying the perpendicular components of the radial arm and the force. Okay? Now, torque is also equal to I times alpha. So if you're using the torque to speed up something spinning and you knew the rotational inertia of what was spinning, then you could solve for alpha. So you could do that too. Set this box equal to this box. Okay? Another classic example besides using a wrench is like opening a door, right? Why is the doorknob opposite the hinges, right? Increase that radial arm. Right. Right-hand roll, we didn't do a whole lot. You could describe torque as clockwise or counterclockwise, but mathematically, there's a lot of convenient reasons why you might want to open up a third axis, like the z-axis. Maybe leave that more for college. How about that? Equilibrium. So the short of equilibrium is that the sum of the force and the sum of the torque goes to 0. There's what it looks like in 2 dimensions and in 3 dimensions. Right? Ooh, you guys had a lab where you guys remember day 2 of your torque lab looked like this. Okay, so the setup here is that the forces have to sum to 0, but also the torque has to sum to 0. Now, the forces sum to 0 means that the 2 tensions up equals the 2 weights down. Okay? You know, another place you guys saw this besides your lab, right, was you guys remember the Paul Hewitt story? He's walking around the scaffolding with his friend. There's, hey, what's happening to the tensions in the ropes as we're walking along? Okay? Okay. But to really solve the rest of this, the whole, because if you just had this top equation, you wouldn't be able to solve it by itself. You need to bring in torque. Okay? And torque is radial arm crossed with the force. And what you usually do is, you can pick any point as the pivot point, but usually there's a convenient point. Like if I pick this point right here, now one of the unknown forces just causes 0 torque at that point, like pushing on the door hinges of the door, right? And you can solve for the other unknown, and then you go back and solve the whole thing. Okay? So that could be set up to solve that. Torque and angular momentum are related to each other. If this is constant torque for some time, you're building up the angular momentum. Okay? The area of one and the slope of the other. They're related to each other. If you know one, you know the other. Right? Spin a basketball. So suppose they put torque times time is changing angular momentum, exactly like that last slide showed with the graphs. So r cross f is the torque, I times omega is the angular momentum, final angular momentum. Substitute in for the basketball, rotational inertia, and bam, there's how fast the basketball is spinning. Give a little hit, it's going to spin that fast right there. Angular momentum, ice skater, the fact that it's conserved. You guys know if you go into rotation, you pull your arms in, change your rotational inertia, you're going to speed up spinning. Right, got it. You guys remember this one? For a point mass, it's regular momentum times the radial arm, MVR. Right. It's just got a few slides left here. Ball rolls downhill. Show you guys a couple of perspectives. A question might be like, how fast is it going at the bottom? You can do free body diagram, have it rolling, just 5/3 comes from parallel axis theorem for like rolling on, right? You get here, that's the speed at the bottom, right? But I think there's a better, faster way to solve it, way I prefer to solve it, which is this slide right here, conservation of energy. You do conservation of energy, you actually get to the result a lot faster. It's the same answer, regardless of how you solve it. Right? That's a common theme in physics, right? Multiple paths through the forest lead you to the same outcome. Okay? And finally, last slide right here. You guys know this whole presentation's on Google Classroom. You go back to it again, animation, the whole thing. I suppose there's a roll race, all these different objects. Now, actually, there's one object that's not rolling. That's this air hockey puck. And that's the only lane that has no friction. And there is static friction everywhere else, right? But one frictionless lane. Now, the frictionless one is going to win the race, right? Because all of its potential energy turns into translational kinetic. But those other objects, some of their energy is going to go into making them roll, right? Now, the bowling ball is going to win the race for all the rolling objects because it has the smallest rotational inertia. And then each of these objects successfully has more rotational inertia, therefore more energy gets diverted into making it roll. And that ring is always going to lose the race. Now, even if these objects are crazy different masses and radial sizes, That doesn't matter. Like a marble and a bowling ball would go down side by side because those are both solid spheres. So it has to do with how the mass is distributed. All right, and that is exactly the end of the presentation, which is perfect because we got about 10 seconds till the bell. Okay. So tomorrow, you guys know we're going to hit those conceptual questions. Okay. You guys have a great rest of your day.